Welcome back from a wonderful break of a weekend. We talked last week about transformations of functions and how those apply to transformations of trig functions. Before that, we talked about the general definition of trig functions and how to work with them. So now, what do you think we're going to work on? That's right, trig identities. So what are trig identities? Well, it's kind of like proving things. Usually they ask you to show stuff. Instead, show this identity is true or verify the following identity, as opposed to just saying the big nasty word that a lot of people freak out about, prove. Well, there's one thing that's really nice about trig proofs is you don't have to do a whole lot. It's more of just checking to make sure that you know what you're doing. It's not the big formal stuff like prove that the square root of 2 is irrational. I've done it. It's kind of cool if you get it. If you don't get it, it's just really confusing. Anyway, there's a reason they don't use the word prove, and that's because they're like baby proofs. So, all right, where do we begin? Well, as with most things in trig or geometry, we start with a circle. Not just any circle, a circle in the coordinate plane. So this is a circle in the coordinate plane of radius r. So this point here would be r comma 0. And then here we could talk about this being 0 comma r. Now let's make an actual, I don't know, triangle here. So since we're talking about trig, maybe you should have a triangle. So here is our right triangle for some arbitrary angle theta. I'll draw theta in for you. There's theta. Okay, so let's label the points. Let's say that this is arbitrarily length x, and say that this height here is y. Well, there, I'll make that a right angle. And then we know that this is length r, because it's the hypotenuse, but it's spanning from the origin of the circle out here to the edge. And remember, what's the definition of a circle? Given a point and a distance is the collection of all points that are equidistant from the central point. Equidistant equal to a certain distance, the distance given. But anyway, so this point, because it's on the edge of the circle, has to be r units away from the origin. So what do we know? Well, from high school and Algebra 2 or Math B or Math 3 or 4 or pre-calculus or whatever class you took, we know that x squared plus y squared is equal to r squared. What's this called? Right, the Pythagorean theorem. Pythagoras, he's a really interesting guy. He actually had a cult where he believed that there were special characteristics to numbers, and he didn't believe in numbers that weren't natural. So, irrational numbers, so like the square root of 2, didn't exist. Zero didn't exist. And negative numbers didn't exist. And if you tried to claim that they did exist, then, well, they'd kill you. Now, the Pythagorean theorem is attributed to Pythagoras, but that doesn't actually mean that Pythagoras is the one that came up with the Pythagorean theorem. Many scholars believe the Pythagorean theorem was actually derived by one of Pythagoras' followers, but like many cults, they just attributed all of their great works to their master. So we don't really know what Pythagoras could do mathematically. We just know that he was incredibly crazy. So yeah, if you believed in things that we now take for granted now, like negative numbers 0, he would kill you. They would actually take a dagger and they would murder you. And that's part of what made them a cult. Something else that's odd about Pythagoras, as I'm going on about him, is that he thought that beans, like lentils, like beans, um, beans, so beans, like that's a green bean, okay? Um, he thought that they were unholy and unnatural because when you ate them, well, they tended to create gas. So there's a story that because the Pythagorean cult was so selective, they didn't let just anybody into the cult. You had to prove yourself worthy. That they didn't let people in, and that made people angry because Pythagoras was being selective. He had a clique, and where all the cool people were. So they got very mad that he wouldn't let them in, so they burned his place down. They actually burned his house where him and all of his followers were staying. They killed a bunch of his followers, and Pythagoras escaped out the back. So he's being chased by an angry mob. You can imagine like swords and pitchforks and torches and things. And he came across a field of beans. And he had a choice. He could either cross the field of beans and save his life, or he could not cross the field of beans and get cut down. Well, Pythagoras, being the crazy nut job that he was, didn't cross the field of beans, and he got cut down. And that's where Pythagoras ended. So that was a long diatribe, but you learned a little bit about Pythagoras, the alleged founder of the Pythagorean theorem. So we have this x squared plus y squared equals r squared. Well, that doesn't tell us a whole lot. But we know that we have this triangle here in the quadrant 1 associated with angle theta of sides length x and y and then hypotenuse length r. So what we do know about triangles like this are ratios. And the ratios are related to the angles by these wonderful little functions called trig functions. And this is what we've been talking about. So I'm just going to quickly jot this out. Cosine x over r. And tangent of theta is equal to sine theta over cosine theta equals just y over x. Okay, so we know all this. Now, say we wanted to relate these two things. So we have these relationships, then we have the Pythagorean theorem. How are they related? Well, let's try solving this top equation for y. So this means that y is equal to r times sine of theta. And this one, this double arrow thing is an imply symbol. This says that x is equal to r cosine theta. And tangent we don't really care about right now. You see that that's actually sine over cosine, which we already have there. So now substitute these values into the Pythagorean theorem over here on the right-hand side. And what do you get? You get r cosine theta squared plus r sine theta squared, ignore that dot, equals r squared. So now if you distribute this, you end up with r squared cosine squared theta plus r squared sine squared theta equals r squared. Now, brief aside, why am I writing cosine squared theta instead of cosine of theta squared? Well, the second one here, this could mean cosine of theta squared, or it could mean cosine of theta quantity squared, or something else that we haven't defined. Because remember, like square root, or when we have roots, cubed roots, the threes, the little superscripts could mean various things. So you say, okay, well, fine, Ben, just put in parentheses. That way we know that it's the quantity of cosine of theta squared. Well, see, but then if we do that, then we have to add in these parentheses. And mathematicians, they're inherently lazy. So it's easier just to say cosine squared of theta. If you really want to, you can put the parentheses in here. But the general notation has the name of the function, the squared symbol, and then the independent variable. Interesting, though, because we don't generally do that for other functions. F's